Okay, this is 1.5, inverse relations. Who would like to read? Yeah, Ramon, thank you.
The owner of a candy company are creating a spherical container to hold their small chocolates. They are trying to decide what size to make the sphere and how much volume the sphere will hold based on its radius. The volume of a sphere is given by the relationship V equals 4 over 3 pi r root.
Okay, so they're making a spherical container and they're going to put chocolates in it. Okay, this formula for volume is a universally known and accepted formula. Okay, what we're studying today is called inverse relations. So we have a relation here that gives us our radius in terms of our volume. Okay, so the question says, how can we use this relationship to find the radius of a sphere for a given volume? So this particular manufacturing company's problem is they have the volume, but they want to know the radius to build their equipment to. Okay, so this formula doesn't really help, right? Because if we have the radius with this formula, we can calculate the volume very easily. But they actually want to know the radius, and they have the volume. So if I say volume is equal to, let's just throw out a number, 2,000 centimeters cubed. Okay? What's my radius? Who can tell me? Yeah.
Wouldn't it be radius is equal to volume divided by, wait, never mind.
Yeah, you're exactly on the right track, and you got to the point that I was hoping you would, where you said, okay, wait, never mind. It gets a little complicated, right? He's on the right track, Elijah. What he's trying to do is he's trying to solve to leave radius on its own. Can anyone do that? Yeah. Okay. Go ahead. Yeah. Yeah. Go. So here, I'll help you out. So we're gonna sub in 2,000 for volume, right? And now we're left with this. Okay. Now what?
Well, you basically divide the volume by r cubed.
Okay.
So you isolate it on that side.
You're doing this, right?
Yep.
Okay. Good.
Now to get rid of the 2,000, you have to divide that by 1 over, times it by 1 over 2,000.
Okay.
So now you're left with r cubed. You got cube already?
Yes.
And now you basically get the cubic root
Okay.
of 1 over r cubed.
It's really messy, right? I'm gonna stop him there. He's on the right track. He made a little mistake just off the start. Is he moved the r cubed? He wanted it on the left-hand side, but by doing so, he moved it to the denominator, and we don't want that. Okay, so this is what we would have done. I'll do it again over here. So 2,000, very close. Just on the right track, and would have likely got the same answer. But what I would have done, I would have left the r cube over here and just taken this, which is essentially just a constant. Right, it's just a number. We know pi is 3.14. So we're going to move that to the other side, or divide 2,000 by this whole value. Okay, so that way this whole value crosses out, and I'm left with this. So 2,000 divided by 4/3 pi. 177, thank you. 477 is equal. Okay, is equal to r cubed, and then we take the cube root like he did of both sides. So we're left with r, and I just left it on the right hand side because that's where it was, is equal to, and what's the cube root of 477.46? 7.82. Okay, very good. So now we have our radius, 7.82, and that's in centimeters. Okay, and of course I could write this way. Okay, if we wanted the variable on the left-hand side, doesn't matter. Okay? Which is all great and fine and dandy. The problem then becomes is, what if I tell you now, oh, wait a minute, the volume is not 2,000, it's actually 1,800. So yeah, we go back and we have to do all this mumbo jumbo again, okay? And that's the whole point of today's lesson, is that we don't want to have to do this every time. So we want to isolate r in terms of v without substituting in the value of v. Okay, and if we can do that, that's called an inverse relation. So we're giving a relation and we're just switching them around. Okay, so let's do it one more time. This time, I'm gonna leave v in there. So v is equal to 4/3 pi r cubed. R cubed is equal to v, and now I'm gonna multiply by 3. So that cancels this 3 out. And divide by 4, so that cancels this 4 out, and then also divide by pi. Everybody follow that? So to get rid of this 4/3, I multiplied both by 3/4, so that canceled out, and this pi was on the numerator, it comes on the denominator, dividing both sides by pi. All right, and finally the last step is I take the cube root of this. Do I have to put plus or minus here?
Where?
Here, plus or minus. No, I don't. Okay, if it was a square, I would, because a negative squared also gives us a positive value, but because it's a cube, I don't have to put that. Okay, we'll talk about that a little bit more when we get to a square. Any questions here? So how I did this?
So, sir, you basically just moved the equation around.
Yes. Okay, so as I've told you before, I prefer algebra over graphing or table of values. Here they actually use a table of values. So the first thing they do is they just substitute in 0 to 10 for the radius, and they calculate the volume, and then they plot it. So this is the graph of this, okay, as is. Okay, any questions there, what they've done? All right, you guys can replicate that. I would hope no problem, right? You're just taking value of r, you're substituting in, and then making the calculations to find the volume. When r is 0, v is 0, etc. All right? No questions there. Okay, now what they're going to do. So it says to graph the radius in terms of the volume, switch the variables in the table. So they're taking these same variables now that they found, and they're just switching the v and the r. So what was radius before was our x values. They're making radius our y values and volume our x values. So see, these values are the same, right? 0, 0, 0, 0, 1, 4.2, 1, 4.2. They're just switching them, okay? So what they've done essentially is they switched the axis around, okay? So volume is here now on the y, and radius is on the x. Volume is on the x, and now radius is on the y. Okay? And the reason they do that is because this graph now is the inverse function of this graph. Or another way to think of it is this graph is this.
I can't see it.
Okay, I'm bringing it down. Hold on. This graph is this. Okay? Where now r is the y variable or dependent, and v is the independent. Okay, which is the opposite of what was happening over here. Okay, here we had v as the dependent and r as the independent. Does that make sense to you guys? Any questions? That's all they've done. They've switched them. Okay, now this graph, what they're showing here, and keep in mind it's very blown out. Okay, it's very drawn back, so to speak. They've graphed both of them. So they've put this graph and this graph on one graph. So this graph is both of these on here. Okay, with just different units. Okay, and they actually say we ignore units. Okay, the reason why they say they ignore units is because the axes are opposite, right? This radius would be on the y. So they're just plotting them out. So see, that graph is there in blue. That graph in red is in red here. Okay, what they find is that there's a relationship between these two. And they write it there, y equals x, but they didn't draw it, so I just drew it out. There's our y equals x line. So between the regular relation and the inverse relation, there's a reflection happening, and it's across y equals x. Okay? So it says the inverse was found by switching the independent and dependent variables in the table of values. The independent and dependent variables can also be switched in the equation of the relation to determine the equation of the inverse relation. And that's what I did right here. Okay? That's what I did up there. And I believe they're going to do that. Let's see. Yes. So it says, number 2. Recall that the volume of a sphere is given by the relationship this. Determine the equation of the inverse. So I did this already, right? So 3. Here it is broken down into a few more steps. But they end up with the same equation that I had. Okay? All right, let's just do the reflecting quickly. Compare the domain and range of this function and its inverse. So let's look at the graphs again. So the domain, so all the x values, how do they compare? Gianluca. This graph and this graph, how do the domains compare? Right, if you compare the domain and the range, they do switch. Good. So here, our domain is x values all greater than 0, and our range is x value, or sorry, y values here greater than 0.
Aren't they both the same? Yeah.
You're right. They are the same for this particular function. We'll show you when we do the inverse. They actually do switch. The reason why they're the same is because in the initial graph, the domain and range are the same. They're the same. So when you switch them, they're still the same. Okay? What you're going to see, I'll show you in the next example, the domain and range switch. So what was previously the domain becomes the range in the inverse function. What was previously the range in the original function comes the domain. Okay? Let me show you that. Makes a little more sense. We go to the next example. Yeah, it does. Okay? Let's talk about this. I'll just skip to that point that I was making right away. So the blue graph is the original function, and the red graph is the inverse. Okay, so again, it's reflected upon the line y equals x. Okay. The range of the original function was what? What was the range? Kevin.
The range of the original function was y is an element of all real numbers and y is greater than 0.
Excellent. Good. So that's the range. What is the domain of the red function or the inverse function? Yep.
The domain is the old range, the range of the
Which is what?
So all x values are greater or equal to 0.
Yes. Good. Very good. Excellent. So do you see how what was the range greater than and equal to 0 now becomes the domain? And what was the original domain, which was all real numbers, now becomes the range, all real numbers, in the inverse function. Okay? So they do switch. The first example was a little confusing because the domain and range were identical. In this case, on the original function, the domain and range are different. Okay? Let's see what we're talking about in this example. It says, given f at x is x squared, find the inverse relation. Compare the domain and range of the function and its inverse. So we did that. We've done that one. And determine if the inverse relation is also a function. So let's do C first. Is the inverse a function? Is this a function in red?
No.
No, why?
It is random.
Excellent. Vertical line test hits twice. Okay? Another way of saying that, for one value of x, there's two different values of y. So it's not a function. Okay, finally the last one, find the inverse. So here's the process, guys. This process stays the same for no matter how complex the original equation is. Okay, here it is. Very, very important, this part here. Okay? And it's simple, but you need to know the steps. The first one is to rewrite the function using x and y. So if there's function notation, f at x, they take it out. They put it back to y. Okay, the reason why they do that is because it just gets too confusing. Okay, that's the only reason. So what was f at x? We go back to y. The next step they take, so 1, change f at x to y. F at x goes to y. Next, 2, interchange x and y in the relation. Okay? So the reason we do this, so what was once y becomes x, and what was once x becomes y. The reason we do this is because we're changing the axes. So we want the y to continue to be dependent, and we want the x to continue to be independent. Otherwise, again, it's going to get very confusing. Okay? So that's the reason they change the variables. And then the last step, which is arguably the hardest, they solve for the y. Okay, so they need to take the square root of both sides. In this case, because it's a square, we need to put plus or minus here in front of the square root. Everybody tell me why? Yeah.
Because when you take the square root of a number, it could be either positive or negative.
Right, because negative 4 times negative 4 is 16. And 4 times 4 is also 16. So the square root of 16 is plus or minus 4. Okay? That's why this plus or minus comes in here. Okay, and you have to do that. You don't have to do that if it's a cube root, because there's only one number that cubes to itself to get that final number. Okay? But square, you have to consider that. So because of that, and because of that, we know that this is not a function. Because whenever we have plus or minus, there's two possible values for y for one value of x. So that's also why it's not a function. So there is the reason algebraically not a function. Okay? And this is the reason the vertical line test is the reason graphically it's not a function. Any questions?
So, sir, if it both has a plus or minus sign in front, it's not a function.
Right. Yeah, it's not a function because if I plug in a value here of 4 for x, there's two possible y values. There's negative 2 and 2. Yes,
So
Luigi.
for the parent functions that you gave us, why didn't we do the plus or minus?
Which parent function?
When you gave us the sheet with the parent functions like 2 days ago.
Because this is not a parent function.
Okay, so the parent function of root x, the plus or minus wouldn't apply?
No, because it's only considering the positive side of that function.
Okay.
Because
Oh,
this,
you said
okay, it's a good question. This is a parent function. This is not. This is not a function at all. Okay, because it doesn't satisfy the vertical line test.
So the reason we did that was because there was a limitation on the y, because y had to be greater than 0.
The reason we did what?
We didn't put the plus or minus for y equals x. Y
This one?
Yeah.
Because that's the parent function.
Yeah.
That's the reason it was chosen. It was one of the ones that was chosen as a parent function. It was graphed. It's positive root x. Okay? This is also a function. Right? This is the same function. This is the parent function, and this is a reflection in the x-axis. So this is a function. This is a function. This is not. Can't have both at the same time. Okay?
Yeah.
Got it. Another question? No? All right. Last example. Then we're going to get to the quiz. Archaeologists use models for relationships between height and footprint length to determine the height of a person. So they get this equation here where h is your height and x is your footprint. It's not necessarily always true, right? There's some people that are shorter that have bigger feet. Okay, but generally speaking, on average, if you're very, very, very tall, you generally tend to have a larger foot size. Okay, like Shaq wears size 14 or whatever it is. Okay, he wears 20? All right. Yeah, it's something big. Okay, so here's our formula that they've developed. Now, what it's saying is says to predict the footprint length, rewrite the relationship with footprint length as a dependent variable and h at x as the independent variable. So they came up with this equation because the archaeologists were actually interested more in the height, and they could only find footprints, right? Obviously, they couldn't measure the height because the people didn't exist anymore. So they lined up the equation like this, which makes a lot of sense. But now let's say that they want to know the footprint for a specific height. So they need to reverse the equation. That's the whole reason we do this. Okay, so we take the steps that we know. We change h at x to y. That's the first step. So there it is there. The next step is we flip y and x. So y becomes x becomes y. And finally, we solve for y. Okay, they leave y on the right-hand side, and then they make the correct reverse operations to solve for y. Very simple math here. Notice the function notation here. They're saying that y is equal to this. It's also equal to h negative 1x. That's saying the inverse of the original function x. So h negative 1x is inverse of original function x. This is very important, okay? Because when you see this on the quiz or the test, you need to know what it means. Joseph.
So when you're asking for the inverse, can we just put y equals, or do we have to put h negative x?
You have to know what both means. You have to know this, okay?
But I'm saying when you ask us to write it out, are we going to get marked off if we don't put h negative x? Or like y negative, sorry, f negative x?
Not so much that you're going to get marked off, but if I ask you about this, if I say find this value and you don't know what this means, then you won't be able to do it, okay? So it says when an inverse relation is also a function, the notation f at negative 1x can be used to define the inverse function. It's important that we understand that. So there's our inverse function at the value of 170. So we're subbing in the value now of the height, and they solve for the footprint length. Okay, so it's just taking the equation that is established or given, reversing it so you can sub in what was the independent variable now as the independent variable. So the inverse function f at x is denoted by f at negative 1x. So there it is in red. And can be used as inverse. The graph of the inverse function is a reflection of the line y equals x. Any questions? One more point and then we'll start the quiz. Not all inverse relations are functions. The domain and range of the original function may need to get restricted to ensure that the inverse of a function is also a function. That's when we did this, right? We flipped this to this. It no longer became a function because of the vertical line test. To find the inverse algebraically, write the function equation using y instead of f at x, interchange x and y, and solve for y. Maybe the most important part of this lesson. If AB represents a point on the graph f at x, then BA represents a point on the graph of the corresponding f at negative 1. Very, very interesting to know that. Okay, if we have a point on the original function, we can reverse the x and y values and we'll have the point on the inverse function. Given a table of values or a graph of a function, the independent and dependent variables can be interchanged to get a table of values or a graph of the inverse relation. That's from the first example. And the domain of a function is the range of its inverse. And the range of a function is the domain of its inverse. All right, no more questions? Okay, we're going to end there. Everything off.